On June 19, 1947, the leaders of more than 60 Soviet industrial ministries were finally able to breathe a sigh of relief. The most important task of the party and the government had been completed. The heavy bomber had entered trials. No one doubted its success. At the Kazan plant, they did not even build experimental prototypes, but immediately laid down the first series of 20 machines. And yet, for the vast complex of 900 enterprises headed by the design bureau of Andrei Nikolaevich Tupolev, the real work was only beginning, and its final outcome was a matter of life and death in the unstable post-war world. It was no accident that the omnipotent Beria was appointed as overseer. Circumstances forced the experienced designers to abandon their own concepts and take on the task of repeating another's path. Tupolev's team had to leave their aircraft, the production preparation for which had already begun, and the factories had to master new technologies and materials. Huge sealed cabins, a multitude of complex mechanisms and electronic systems seemed like otherworldly technical marvels. But all of this turned out to be carefully thought out and adapted for mass production. Problems that arose here and there were solved on site under the leadership of the chief designer of the machine, Dmitry Sergeyevich Markov, and the general designer, Andrei Nikolaevich Tupolev. In the spring of 1947, the first aircraft was ready. The crew, formed from plant personnel, was headed by one of the most experienced test pilots of the Flight Research Institute, Nikolai Semenovich Rybko. Soon, the machine was ferried to the Institute airfield in Zhukovsky, where the main program of state trials began. No particular surprises were expected. The aircraft's stability and controllability proved to be within normal limits, and overall, Rybko gave a fairly accurate assessment of the machine when he counseled the pilot, appointed commander of the second aircraft, Mark Lazarovich Galai. The engines are fine, they work, the controls are a little stiff, especially on roll. Either the cables have stretched or the friction in the rollers is too great. But overall, to turn the control column, one must work. Equipment? Imagine, it seems to operate. At least what we have already switched on. The appearance of the second and then the third aircraft made it possible to accelerate the test program. Despite their tight schedule, all three aircraft and their sibling took part in the August Air Parade of 1947. However, not everything went smoothly. Soon the third machine was lost due to an engine fire. Its commander, Anatoly Grigorovich Vasilchenko, having failed to reach the runway, landed on the fuselage. The aircraft could not be repaired. The fourth aircraft from the first series received the first major improvement, a cannon defensive armament system. On the first three aircraft, following the example of the American bomber, they installed 11 machine guns of caliber 0.50 inches. In the tail installation, they placed 3 barrels. Already at the meeting devoted to preparing the decree on construction of the first series, Tupolev proposed to equip the aircraft with guns of caliber 23 mm, demanding that the developers, the Design Bureau of the People's Commissariat of Armaments and designers Aaron Aronovich Nudelman and Alexander Aronovich Richter, speed up the finalization of this artillery system. Machine guns could no longer be a reliable defense, but post-war generation cannons were not yet ready. They then decided to use a gun whose weight and installation dimensions were close to those of a machine gun. The creation of the armament system was headed by Anatoly Vasilyevich Nadashkevich, Tupolev's deputy for armament. The commander of the fourth aircraft was appointed to be a naval aviation pilot, Vladimir Petrovich Marunov. Operational pilots and pilots from the Air Force Research Institute began to be involved in the trials. The aircraft was being prepared for acceptance, although there remained many problems. Perhaps the greatest difficulties were created by the power plant, which was unprecedentedly complex. The engines even contained electronics, tube amplifiers that worked in the supercharging control system. Turbochargers also caused a great deal of trouble. During one of the test flights, the crew of the Air Force Research Institute, Commander Sergei Mikhailovich Antonov, lead engineer Ispirian, experienced a fire in the second engine. The engine was shut down, fire extinguishers were activated, they tried to put out the flames with a sharp glide, but to no avail. Moreover, before long, a third engine began to smoke. Streams of gasoline and oil were leaking from its nacelle. The RPM fell, but the aircraft still hauled on 2 engines. There was the runway ahead. The crew managed to land the mangled aircraft. After inspection, it turned out that the connecting rod on the second engine had broken and the compressor on the third had come apart, shredding the fuselage, the tanks, and the pipelines. Another misfortune was a propeller overspeed in flight. On the second aircraft, this led to engine failure, and on the fourth, the propeller even disintegrated, with the blades flying off and damaging the wing and the adjacent engine nacelle. And yet, the matter was approaching the finish. The second prototype was the first to complete the flight program, while Galley received the final main aircraft, the 20th. In 1948, the airplane was officially given the name Tu-4, and at the end of that same year, Stalin personally signed the act approving the completion of the state trials, while the factory already had the first production batch of 10 bombers ready for transfer to combat units. For re-equipping with the Tu-4, the 13th Long-Range Bomber Division was chosen, and the lead unit became the 185th Guards Aviation Regiment, stationed in Poltava. Training took place in Kazan at the base of the 890th Long-Range Bomber Regiment, which was converted into a training unit. The pilots of that unit had extensive experience flying American heavy bombers, which allowed them to be the first among combat crews to master the Tu-4. The Liberators were widely used to train pilots in handling heavy aircraft with a nose-wheel landing gear. The regiment provided Tu-4 crew training until 1955, when Jet Tu-16s began to arrive. In April of 1949, the Tu-4s arrived in Poltava, and in May, the retraining of the 185th Regiment was completed. The deployment of the new bombers continued. First of all, units in the western direction were re-equipped. Regiments that received the Tu-4 were redesignated as heavy bomber regiments. Their mission was to destroy the most important military and industrial targets on enemy territory, to deliver massive strikes against political and economic centers and directly against enemy forces. For this purpose, it was planned to use bases in East Germany and in the countries of Eastern Europe. In various configurations, the Tu-4 could carry heavy bombs weighing 6,600 and 3,300 pounds, as well as weapons of mass destruction, chemical munitions filled with a concentrated mixture of mustard gas and lewisite with a persistence period of not less than 3 days. But the main weapon was to be the atomic bomb, the development of which was nearing completion. Aircraft delivered to naval aviation units were armed with armor-piercing aerial bombs weighing 1,100 and 2,200 pounds, intended to strike large warships and heavily protected structures, as well as moored and bottom-laid mines. Bomb release was carried out singly, in series or in salvo by means of an electric release mechanism. The automatic sight allowed bombing at any speed and altitude, and in conditions of no visibility, the radar station Cobalt came into play. The onboard radar, whose development was handled by the design bureau of the Leningrad electromechanical plant, now the company Leninets Holding, led by Andrei Ivanovich Korchmar and Yakov Borisovich Shapirovsky, fundamentally changed the tactics of bomber aviation. It made possible bombing in bad weather, and at night from altitudes ranging from 9,800 feet up to the ceiling. Cobalt could detect a large industrial building from a distance of 62 miles and determine its coordinates with an accuracy of plus or minus 2 degrees in azimuth and plus or minus 330 feet in range, while its maximum operating range was 248 miles. Radar could also be used to determine the aircraft's position by comparing the image on the screen with an ordinary map. The navigation system included a radio compass, gyroscopic and magnetic compasses, and an autopilot. The radio compass worked together with a marker radio receiver, a rangefinder that determined the distance to the start of the runway, and course and glide slope equipment. The whole system was used for blind landings and made it possible to land the aircraft safely with cloud base at 656 feet and visibility of 6,562 feet. Deploying Tu-4 aircraft required equipping airbases with special radio stations. 2 were installed for each direction along the runway axis, range relay stations, light command equipment, and permanent command and control centers. The crews of the 52nd Guards Heavy Bomber Aviation Regiment were the first to master the blind landing system at the end of 1949, and beginning in 1950, aircraft began to arrive equipped with the new blind landing system called Matarik, which lowered the minimum meteorological conditions to 328 feet cloud base and 3,281 feet visibility. The airborne equipment was supplemented with radio altimeters called LITI. The large amount of complex equipment created its own difficulties. It was necessary to sharply raise the level of personnel training, especially for radio operators. They had to not only acquire knowledge, but, as people said, get a lot of hands-on practice. For example, the radar receiver was tuned by maximizing the current in the detector called crystal, and if the operator turned the tuning knob too far, he would skip past the optimal value and reception would worsen. Because of this, they would usually say, "The current in the crystal is a bit low. The operator is no good." The organization of the air defense complex was also changed. Now, using one of the aiming stations, fire could be controlled from any firing point. Admittedly, adjusting and zeroing the system was a complicated and labor-intensive procedure. Technicians who serviced the aircraft and engines had a hard time as well. For example, many structural bolts were pressed in with considerable interference fit and could only be removed by drilling them out, and they were made of very hard chrome molybdenum steel. When removing skin panels of the center wing under the consoles, it was necessary to set special jacks. Otherwise, the wing could fold under its own weight. And even just tightening the heavy covers while climbing high on shaky ladders was an ordeal. However, those who came to serve on the Tu-4 did not face only difficulties. Most instruments and equipment were placed conveniently and were easily accessible. Pressurized cabins provided unprecedented comfort, and their equipment even included thermoses for hot food and sleeping places for crew members. Even natural needs were taken care of. 3 toilet buckets and a tank fitted with special lids provided reasonably clean air in the cabins. Overall, the aircraft immediately commanded genuine respect. Almost immediately after the start of serial production, improvements were made to the Tu-4 design that enhanced its combat effectiveness and operational suitability. These changes usually appeared first on aircraft from Factory 22, and then on the 2 other enterprises that switched to production of the new aircraft. These were Factory 18 in Kuybyshev and Factory 23 in the Moscow suburb of Fili. One of the first such changes was the introduction of a 2-gun tail installation, which, while lighter in weight, had a wider field of fire. Later, separate transmission antennas for the Maginai-J airborne radar identification station were introduced, which improved the system's performance. Some changes were temporary in nature. Thus, beginning with aircraft of the 19th series, an additional command radio station began to be installed, which was caused by the need to provide control of a large group of aircraft in the aerodrome area, where communication channels were extremely overloaded. Let's begin with radio communications. Early aircraft were fitted with a radio copied from an American example, even retaining the original designation. But soon it was replaced by a Soviet development with a domestically produced receiver, and the additional radio socket was eventually abandoned altogether. Other innovations proved more successful. For example, electric artificial horizons replaced the old vacuum instruments. This greatly eased the pilot's workload. One of the next production series turned out to be the richest in improvements. Light filters and protective curtains were installed for the pilots and the navigator. The seats for the radio operator, the wireless operator, and the flight engineer were made more comfortable. Now they could be adjusted in height. The same aircraft received a navigation coordinator. It was the first Soviet onboard computer based on vacuum tubes, which allowed calculation of the distance traveled and continuous determination of coordinates. In those years, cybernetics in the Soviet Union was considered a pseudoscience, and the very term computing machine aroused suspicion. Therefore, a neutral name had to be coined for this device. All bombers had a photo hatch with a tilting frame and a command instrument, but at first the aircraft had to be outfitted with photographic equipment in the units, with whatever was at hand. Only later did machines leave the factory already equipped with aerial cameras. Every third aircraft received an automatic camera with a 100-centimeter lens, optimized for work from high altitude. 2 others received a less powerful camera with a 75-centimeter lens. In addition, a night camera with a 4-lens objective was added to each machine, a fully automatic device whose exposure was triggered by the flash of a photobomb. These cameras were intended to record bombing results and to photograph small objects. For photographing short routes, a movie camera was used, which belonged to each aircraft. And finally, another improvement was made, for now in advance. Due to the planned installation of more powerful guns, the fuselage structure was significantly reinforced. The new guns had longer barrels, which led to the introduction of a lock that prevented opening of the first bomb bay when the lower nose turret was in the transit position with the barrels pointing rearward. At the same time, folding hatches were fitted on the flaps of that compartment to allow the barrels to pass in case the lock failed. To compensate for the loss of stiffness of the flaps, additional supports for their open position were introduced. Several samples of gun and cannon armament were proposed for this bomber. For example, a very high rate of fire large-caliber machine gun of the Afanasiev system and a 23mm cannon developed by the Design Bureau under the leadership of Shpetalny. However, Tupolev made his choice. On first inspecting the experimental cannon, he slapped his hand on the cover of the ammunition feed and said, "This is what must be done. This will be the thing." The Minister of Armaments, Dmitry Fedorovich Ustinov, declared refinement of the system the #1 task for his department. Even before the end of trials, he allocated a special plant for series production. In serial production, the cannon was assigned a new index. The design bureaus received overall and installation drawings, and the remaining shortcomings were planned to be eliminated in the course of mastering serial production. When issuing the technical assignment, they approved a predicted service life of the cannon of 6,000 rounds. The first samples barely managed 700 to 1,000. The design had to be changed so that the external appearance of the cannon remained the same. The system's life was first raised to 3,000 and then to the planned 6,000 rounds. The recoil of the NR-23 gun in the first production series exceeded 11,000 pounds of force, varied greatly from example to example, and tended to increase as the ammunition was expended. This caused the mount to become increasingly unstable during firing. Acceptance was halted, and the heads of the Design Bureau were summoned onto the carpet by Deputy Chairman of the Council of Ministers Bulganin. To eliminate this problem, the designers proposed fitting a hydraulic shock absorber to the moving barrel of the gun. With it, the recoil stabilized at 5,800 pounds of force, which was even less than that of the Shishvak-20 gun. Admittedly, this unit was not adjusted immediately. The first variant failed in the thermal pressure chamber and had to be redesigned. The development of the new gun armament system for the Tu-4, which received the designation PV-23 Zirka, was led by Ivan Ivanovich Toropov. Active participation was provided by the chief armament specialist of the Design Bureau, Nadashkevich, and the lead aircraft engineer, Markov. In addition to the new guns, improved autoloaders were installed that ensured reliable resumption of fire after passing through dead zones or after a misfire. Each mount received a counter for remaining rounds, and more powerful electric drives eliminated the dependence of barrel traverse speed on the aircraft's speed. The new PS-48M sighting stations improved fire accuracy and the flexibility of control over the entire system. In 1949, several production Tu-4s were equipped with the PV-23 defensive complex with a total ammunition load of 3,150 rounds. It was decided to conduct state trials of the NR-23 on the Tu-4, and Central Asia was chosen as the test site. The conditions were the toughest. The airfield had no concrete surface. By day, there were sand clouds and heat. The aircraft remained aloft for 4 hours, and at altitude, the temperature dropped to -40 degrees Fahrenheit. The weapon was tested in all modes, including abnormal ones, and it performed excellently. Based on the test results, the NR-23 gun was accepted into service and was used on 7 types of production aircraft. The production rate of the gun reached 2,000 units per month. At the end of 1949, the Kazan aircraft plant laid down the first production series of Tu-4s equipped with the PV-23 system. The series received the number 32. At the factories, the new gun began to be installed, starting with certain aircraft. The defensive capability of the bombers increased sharply, but new problems arose. For example, cracks were discovered in the power housings, and this part had to be replaced on 5,000 already delivered guns, including those on the Tu-4. During the introduction of the NR-23 at the plant, the head of the main directorate of Air Force Armament, Rudnev, his deputy, and designers Noodleman and Richter were present on site without leaving. To guarantee product quality, for the first time in the USSR, full oscilloscope recording of the operation of the automatic mechanism of each delivered unit was introduced. Already during serial production, the NR-23 completed its competitive trials together with the SH-23 system, developed at another design bureau. Shpetalny argued that when firing at a right angle to the aircraft axis, the moving barrel of the NR-23 deformed and could jam, whereas his gun with a fixed barrel did not have this drawback. To verify this, ground firings were conducted. A noose, a taut cable simulating the load, was thrown over the NR-23 barrel. It turned out that the barrel bending did not affect the operation of the automatic mechanism. The final stage of the competition consisted of long burst firings. It was considered that a bomber's gun should be able to fire its entire ammunition load in a single burst. The Sh-23 did not withstand this, and the question of its installation on the Tu-4 was not raised again. Service of the Tu-4 was overshadowed by a series of catastrophes caused by engine failures. In connection with this, beginning with certain aircraft, the chromancel engine mounting shackles were replaced with more durable ones made of chrome molybdenum steel. The exhaust system also caused many problems. 7 modifications were made to the design of the ducts across various series. The next step in the development of the Tu-4 was the replacement of the Magni identification radar with its improved version, Magni IM. This modernization was carried out to ensure that the various radio devices on board worked together more harmoniously without interfering with each other. The task was generally solved, but the recognition range decreased from 34 to 22 miles. However, the cathode ray tube became movable, making the operation of the station much more convenient. At the same time, the Barry transponder was also replaced with its upgraded version. The number of simultaneously entered codes was reduced from 6 to 4, with a total of 20 possible variants. A special distress signal was added, the duration of response pulses was shortened, and the recognition and guidance ranges were combined into a single, narrower band. The new equipment began to be installed at other factories as well. With the introduction of the modernized friend or foe system in combat units, additional secrecy training sessions were held. These sessions often amounted to memorizing numerous prohibitions and warnings. To prevent secret equipment from falling into enemy hands, a special pyrotechnic charge was installed. It could be triggered by a button on the left pilot's instrument panel or automatically by an inertia switch in case of a crash or belly landing. The switch had to be activated when flying over enemy territory. This was done by inserting a special plug into its socket. The instruction process was so strict that, in extreme situations, pilots sometimes became confused by the rather simple sequence of actions and ended up detonating the classified units. There were also cases when the inertia switch went off during a rough landing, the pyrotechnic charge was weak, and the explosion could not be heard in the cockpits. To monitor its condition, a special indicator flag was installed, but it was poorly positioned and often broke off due to strong vibrations. Removing the unit for inspection was not only difficult but also dangerous. The friend or foe system remained a constant source of trouble for the crew, and at times it was simply switched off, although this was strictly prohibited. Other measures were also taken to maintain secrecy. For example, each factory had its own structure for serial numbers. Starting from the early 1950s, the first digits on aircraft built in Kuibyshev were replaced, and the Tu-4 itself began to be referred to in documents as the R aircraft. This index remained in use until 1955, when the usual Tu-4 designation was restored. The next step in upgrading the aircraft's equipment was the installation of the improved Cobalt-M radar station. Its power output was increased, the radio frequency unit was modernized, and the overall operating stability was improved. The equipment also became more user-friendly. To create optimal conditions for the antenna's operation, the retractable radome was made taller. Aircraft began receiving it starting from the 50th production series. But due to delays in refining the radar itself, some factories initially continued to install the older version. On these planes, during training flights when cobalt was not planned to be used, a special cover could be attached to the radome bowl to protect it from shell casings ejected from the lower gun turret. Cobalt-M was implemented in later production series. A new intercom system, the SPU-14M, was also introduced, simpler and more reliable than its predecessor. Later, during operational service in military units, some aircraft received a new radar known as rivet. Its characteristics were similar, but thanks to an attachment that allowed connection to the optical bomb sight CZ, the accuracy of bombing improved significantly. Although only a small number of Tu-4s were converted, technicians who knew how to maintain the new radar, nicknamed rubetists, were always in short supply. Beginning with certain later aircraft, an additional rangefinder indicator and a radio altimeter display appeared at the commander's station. The onboard systems were consuming more and more electrical power, which had long required attention. Finally, on subsequent machines, the old generators were replaced with new ones that provided the same voltage at lower revolutions while allowing higher current consumption. The Tu-4 aircraft had powerful bomb armament, but its maximum weight for the first production series was realized only when carrying 8 bombs weighing 3,300 pounds each, or 4 6-ton bombs. This was not always rational. It was impossible to carry especially powerful post-war bombs weighing 13,200 pounds. In connection with this, a new standard bomb armament was introduced. With it, the number of maximum load variants was reduced to 4. It became possible to suspend new bombs with a total weight of up to 23,300 pounds instead of the previous 13,200 pounds with the old bombs. The use of small bombs, including special ones, weighing 220 pounds and 110 pounds was provided for. And finally, on 2 holders, it was possible to suspend new model bombs weighing 6,600 pounds, 11,000 pounds, and 13,200 pounds. The armament system became more reliable and simpler to operate. For example, when suspending bombs of any model, it was no longer necessary to rearrange fittings. The central jettisonable external fuel tank was attached with a standard lock instead of a special one, while the 2 wing tanks, as before, were fastened with bolts. The standard armament, unified with all the new bombers, was implemented on the subsequent aircraft. Loading heavy bombs into the rear compartment proved to be somewhat inconvenient. The radio station antenna that protruded downward interfered particularly. At first it was made removable and later retractable. Starting with the next production series, an additional radio station was excluded from the radio equipment set, and later the possibility was provided to switch the command radio to the fixed cable antenna of the communication station, because its own antenna often broke due to icing. A serious problem turned out to be the inaccuracy of the radio altimeter. Radio operators tinkered with it for a long time, performing various manipulations until they finally arrived at a simple solution. They spread the antennas apart and everything returned to normal. A final major change was made to the Tu-4 airframe. On certain aircraft, the first spar, the nose, and the tip of the stabilizer were reinforced. Many works waited a very long time for their turn. At the very beginning of Tu-4 operation, the position of flight mechanic was introduced, but the seat for him appeared only much later. Until then, the flight mechanic had to spend long hours of flight sitting on his own parachute. The last factory stage of Tu-4 development was the replacement of the old type propellers with new ones that could be feathered in flight. The new propellers were initially installed on a small number of previously built aircraft, and then became standard equipment. In March 1951, one plant was transferred to Myasishchev. In Kuibyshev, preparations began for the serial production of the Tupolev bomber and later, since the future Tu-95. The Kazan plant switched to building jet bombers Tu-16. Production of the Tu-4 was wound down. In total, about 1,000 airframes were built. But refinement of the aircraft continued even after the start of production. Often such works were prompted by tragic circumstances. For example, during the investigation of a number of catastrophes, on landing the aircraft would fall onto a wing or suddenly drop its nose. It was discovered that the rear gunner unintentionally interfered with the aircraft controls. His duties included starting the emergency power unit, for which he had to stand up. In the cramped cockpit, this was very inconvenient, and he instinctively grabbed the control cables. When the cause was discovered, the cables were covered with protective housings. Another direction of improving the machine consisted in increasing its combat effectiveness and creating various modifications. First of all, the capability to employ nuclear weapons was provided. On August 20, 1945, the State Defense Committee of the USSR issued a decree establishing a special committee headed by Lavrenti Pavlovich Beria. The scientific part was led by Igor Vasilievich Kurchatov. The practical side of the matter was handled by the first main directorate under the Council of People's Commissars of the USSR, and in 1946 a design bureau began work that designed the bomb itself. Its head became Yuli Borisovich Khariton, and the design department was headed by Vitaly Abramovich Turbiner. The very first experimental charge was named the Stalin jet engine. Some people expanded the abbreviation as Russia makes it herself, others as Stalin jet engine. On the 29th of August, 1949, the first Soviet atomic bomb was detonated. Although it was exploded on a tower, it was already, in principle, suitable for being dropped from an airplane. The project was based on the American plutonium bomb that had been tested over Nagasaki. Parallel to the design of the warhead, The Design Bureau, together with the Tupolev Design Bureau's Weapons Brigade, modified 3 aircraft for ballistic and hot tests of the new weapon. These aircraft were fitted with the charge activation system and a special bomb holder. The attachments on the first atomic bombs were located across the axis of the device. The only protection for the crew against the then little-studied damaging effects of a nuclear explosion were light shielding screens and special goggles. They began with a large series of drops of mock-up bombs. They tested parachute designs, tail assemblies, radio altimeters by whose signal the bomb was to detonate at a certain height. Strict requirements were imposed on the drop trajectory, which was made more difficult by the bomb's thick and short body. By that time, they had found a way to reduce the bomb's weight and size. But so as not to delay the first tests, all that was postponed. And as a backup, they produced a small series of 5 aerial bombs with the first charge. Although they were intended to arm long-range aviation, they remained where they had been born, in the town of Artemis 16. The next tower explosion took place on the 24th of September, 1951. And finally, on the 18th of October, according to other data, the 17th of October, at 1 o'clock in the afternoon Moscow time, a crew under the command of Colonel Konstantin Urzuntsev dropped the bomb Maria over the test range in the Semipalatinsk area. Its yield was about 30 kilotons, but even that could not yet become a full serial production specimen. The first serial nuclear warhead was the unified 30-kiloton charge intended for rockets and free-falling bombs. Its variant became the basis for the bomb Tatiana, which entered service with long-range and tactical aviation. Externally, it resembled an ordinary high-explosive bomb. Its body became smaller compared with the first one by more than 4 times, and it became leaner, slimming down from 11,000 to 2,600 pounds. The results of the cold tests allowed simplification of the tail assembly design and a return to longitudinal suspension attachments. In 1953, a decision was made to adopt Tatiana into service and to launch its production. The plan was ambitious: to produce 20 bombs per year. Specialists began to be trained in the military units, training aerial bombs were received, and a multitude of trainers were created. A strict order of actions was developed, almost like a ritual, which regulated every step of the personnel, from receiving the combat order to pressing the release button. Still, the military treated the new weapon with distrust, and constant control from the state security organs irritated them, although it was justified. They then decided to stage a field experiment. The site was chosen in the Orenburg region near the Tutskoye station. In the spring of 1954, a test range was built there. The main object was an exact copy of a battalion strongpoint of the United States Army. The plan was this: drop a bomb on it, then carry out an assault aviation strike, and finally attack with the forces of a motor rifle regiment. All this was to take place in the presence of Minister of Defense Bulganin, the commander of the exercises Zhukov, and numerous guests from brotherly countries, for whom shelters were built 2 miles from the forward edge of the American defense. Soon the training began. A mock-up of Tatiana was dropped from a bomber. The results were terrible. Misses reached up to 2,300 feet. With such accuracy, one could have struck even the distinguished guests. Therefore, they decided not to risk it and to use a different aircraft that provided higher bombing accuracy. The task of carrying out the operation was entrusted to first-class pilot Vasily Yakimovich Kuterichev. The combat task was set by Lieutenant General Sudets, who strictly warned there must be no miss. And so, on the 14th of September, 1954, the bomber with a bomb on board took off. The aircraft climbed to an altitude of 26,000 feet, the minimum altitude at which it could escape the blast wave, and settled on a combat course. Cloud cover stood like a solid wall, and the crew navigated by radar data. Only at the last moment did the navigator Vasil Babets catch sight of the ground and the target through a break in the clouds. At 9:33 in the morning, the navigator operator Kiryushkin pressed the release button. Tatiana detonated at an altitude of 1,150 feet. The deviation from the aiming point amounted to 920 feet. A sinister mushroom cloud still climbed upward, and fighters rushed in to attack while infantry rose from the dugouts. The soldiers saw a dreadful sight: ash, death, and destruction. They did not yet know that, having passed through this final circle of hell, they were doomed to fall ill forever with strange ailments, the cause of which was concealed for a long time. The air crews were no exception. Such was the price of nuclear equilibrium. The tests of the first Soviet nuclear warheads forced the Americans to change their approach to planning a possible war against the Soviet Union. A directive of the United States National Security Council dated April 14, 1950, stated that the potential adversary had more than 1,000 bombers and not fewer than 10 atomic bombs. It was emphasized that this fundamentally alters the probable picture of operations in Europe, since NATO military groupings would become primary targets. The old world was becoming a hostage of nuclear confrontation. Under the new conditions, Soviet long-range aviation was tasked with increasing its radius of action. To strike targets across a significant part of Europe, and especially the British Isles, the fuel reserve was insufficient, and in 1948 a resolution was issued to create an aerial refueling system. The work was assigned to Vladimir Sergeyevich Vakhmistrov. Drawing on sparse information about foreign experience, he designed something resembling a hose cone system. Meanwhile, test pilots Ivan Ivanovich Shelest and Vladimir Sergeyevich Vasyanin proposed an original wing-to-wing refueling method. A mock-up installation was tested on one aircraft, and 2 bombers were allocated to create a full-scale prototype. The wing-to-wing refueling system turned out to be very light and simple, especially for the aircraft being refueled. The hose was stowed along the main wing spar, which allowed the tanker's bomb bay to be used for bombs or additional tanks. But crews had to work intensely, far more demanding than with the hose cone system. The Tu-4 refueling system, using the wing-to-wing scheme, successfully passed state trials and in 1951 was accepted into service. Truthfully, there were few aircraft equipped as required. Experimental machines were often used for refueling training. For example, the crews of the 185th Bomber Regiment trained at the airfield of the Flight Research Institute using Tu-4s with mock-up equipment. Development of the hose cone system was completed at the design bureau of Semyon Mikhailovich Alexeyev. The Tu-4 was assigned the role of tanker, and it was intended to refuel jet aircraft. For this purpose, the fuel system was reworked, allocating part of the tanks for jet fuel. The tests involved engineers of the Flight Research Institute Vladimir Yakovich Molochayev and Sergei Nikolaevich Rybakov, test pilots Petro Ivanovich Kazmin, Stepan Fedorovich Mashkovsky, Leonid Vasilievich Chistiakov, and others. 12 Tu-4 aircraft were converted and entered trials in 1952. Later attempts were made to automate the system by developing a cone controllable from the tanker. This work was led by Vladimir Dmitrievich Kurbasov and Yevgen Timofeyevich Berezkin. In practice, however, only automation for locks, valves, and pumps was used. Planning operations deep inside enemy territory required solving the problem of protecting a group of bombers. Various schemes were considered for in-air refueling of escort fighters, as well as options for towed and parasite fighters. The Tupolev, Mikoyan, and Yakovlev design bureaus proposed the Burlaki system. The Tu-4 bomber was fitted with 2 towing cables with lock target devices. After reaching altitude, it would reel out the cables. The fighters would hook onto them, then fire the grabbers, developed by Yakovlev Design Bureau under the name Garpun, and cut their engines. The range of the MiG-15 with auxiliary tanks in this mode increased to almost 2,500 miles, but their cockpits were cold. The heater did not work without the engine, and the tow aircraft overheated its engines and could not keep formation with the other bombers. The system was not adopted. They also considered the problem of a bomber's survival in zones covered by object-based air defenses. This question was mainly of interest to naval specialists who had to deal with heavily defended small moving targets, enemy warships. In the Soviet Union, work on air-launched cruise missiles had been underway before the war, and on May 13, 1946, a decree of the Council of People's Commissars gave a new impetus to the topic. As a result, several weapons complexes were created, the most successful of which was the K-1 Kometa. The carrier became a modification of the Tu-4 designated with the letter K. 2 pylons for mounting cruise missiles appeared under the wing. The Tu-4K took off and proceeded to the search area. In flight, the missiles were refueled from separate tanks in the wing consoles with jet fuel. After detecting and locking onto a target, the radar initiated a launch from a distance of 50 miles. The autopilot steered the missile into the radar station beam and maintained flight so that the carrier, the missile, and the target lay on a single line, guiding according to a three-point scheme. At 12.5 miles from the target, the missile was reacquired by a semi-active seeker head, which provided higher hit accuracy. The lead designer of the carrier was appointed Nadashkevich. In addition to mechanical refinements, the aircraft's radio-electronic equipment was upgraded. The radiation pattern of the Cobalt radar station was changed so that in guidance mode, it could produce a narrow, focused beam. The station received the name Kometa. At the end of 1951, the crew of Vladimir Petrovich Marunov brought the new aircraft to flight tests. Initially, the pilots trained with radio-controlled aircraft that simulated missiles. In the spring of 1952, the first real launch was conducted. As often happens, the first attempt failed. The missile missed the guidance beam and fell into the sea. But after meticulous work, success was achieved. 8 hits out of 12 launches. On November 12, 1952, the Kometa complex successfully passed state trials. The aircraft crew struck a naval target. It was decided to adopt the system into service with the Soviet Navy. Several dozen late-series aircraft were converted into missile carriers. They received a new radar, and the entire complex was given a new designation. The converted aircraft entered service with 2 regiments of the Black Sea Fleet. The missiles had a warhead weighing 1,100 pounds with enormous destructive power. They could be used both against warships and against coastal targets. But Soviet designers were developing even more powerful guided weapons. In 1949, a glide bomb designed by the Design Bureau under the leadership of Alexander Davidovich Naderadze was tested. The next year, the task was set to develop 3 types of heavy-guided bombs. As a result, munitions weighing 4,400 pounds and 11,000 pounds were designed. Their guidance was carried out using a special sight and a radio control channel. The bombs were mounted under the wings. Tests carried out in 1953 ended in failure, and the bomb had to be refined. It was accepted into service only in 1955 under the name Chaika. In 1954, the Condor was tested from aboard an aircraft. It had a design similar to the Seagull. By that time, it had become clear that jet bombers would become the main carriers of guided bombs, and the older aircraft were relegated to serve only as test beds for a television-guided bomb variant. A television camera was installed in the nose of the second Condor, transmitting the image of the target to the carrier aircraft. An operator watching a special screen adjusted the bomb's flight path by sending radio signals to the control surfaces. Television guidance improved the weapon's accuracy and reduced weather-related limitations. But work on guided aerial bombs was soon interrupted. Aviation regiments were never fully equipped with guided aerial bombs, although some units even began to study the new equipment. Experimentally, the aircraft also received another type of guided weapon, air-to-air missiles. Their guidance used the same method, and the onboard radar was modified to produce a narrow beam. Missiles intended to defend the rear hemisphere were mounted under the tail boom, and their guidance and launch were carried out by a radar operator. Aircraft modified in this way served in the 25th Bomber Regiment. However, the innovation did not become widespread. Guidance was constantly lost. Launch range was short, the missiles themselves were expensive, and moreover, they belonged to a different branch, the Air Defense Forces. The emergence of rocket weapons created the need to develop airborne targets. One such target became an unmanned vehicle launched from the carrier aircraft. 6 aircraft were modified for this purpose. Each aircraft could carry 2 targets. Despite structural lightening, weapons, and some equipment were removed, an aircraft with such a load climbed very slowly, 26,000 feet in 2 hours, consuming a large amount of fuel. Because of this, a ground-launched version of the target was developed. In that same year, 1952, a decision was made to convert airframes that had exhausted their service life into target aircraft. The pilot would fly the machine into the firing zone, abandon the aircraft by parachute, and the target would continue to fly according to its program or under commands from a ground control post. One of the main tasks of the Tu-4 from the very beginning was long-range reconnaissance. The first reconnaissance variants, Tu-4R, differed little from standard bombers except for photographic equipment installed in the bomb bay. Cameras of the AFA-33 or AFA-33M type, with lenses approximately 40 inches long, were usually mounted there. Later, night cameras appeared, for example NAFI 5's 100. The large volume of the bomb bay allowed installation of cassettes that held up to 190 frames of film size 12 by 12 inches. In the early 1950s, the Tu-4R was fitted with the PR-1 radio reconnaissance station. It could detect enemy radars operating in the range from 150 to 3,100 megahertz, determine their location, and create jamming noise in frequencies from 2,600 to 3,100 megahertz. Because of this, the station was sometimes called PRD. Beginning in 1954, the aircraft received more powerful SPS-1 systems and later still more modern SPS-2 systems, which were also used on the Tu-16. The bomb bay could also accommodate devices for the deploying passive countermeasures that ejected strips of foil or short glass rods with a metallic coating. This equipment was operated by the radio countermeasures officer and the electronic warfare flight technician. Crews did not much like this equipment, especially the PR-1 station, which took up a lot of space and was installed in place of the rest bunks. During Tu-4R operations, several problems were discovered. At high altitudes, the camera lenses would ice up, and the photographic film became brittle and lost sensitivity. These difficulties were never completely eliminated, but the program of aircraft use continued. Each air army formed a separate long-range reconnaissance regiment equipped with Tu-4. Some bomber units were re-equipped for reconnaissance and radio countermeasures. One such unit was the 202nd Regiment in Myrhorod. It is known that on the border of 1951 to 1952, a squadron of Tu-4 carried out surveillance of sea areas near the Korean peninsula, tracking troop movements in the conflict zone. The Tu-4 was also used for tasks inside the Soviet Union. In the early 1950s, these aircraft performed complete aerial photographic surveys of the country. The work was carried out by civilian crews and was supervised by Lavrentiy Pavlovich Beria. In the mid-1960s, the last training and navigation Tu-4UHS aircraft were withdrawn from service. They had been used to train cadets in radar operation and bomb sites. Cadets sat in the bomb bay and took turns occupying the workstations while performing training tasks. Jet and turboprop aviation gradually replaced the old piston aircraft. However, it was the Tu-4 that became the basis for testing the first gas turbine engines. After an accident of the experimental Tu-95, a flying laboratory designated 94-2 was created on the Tu-4 platform to test the new Tu-TF-2F engine. The chief engineer was David Israilovich Kontor, and the flight crew commander was Mikhail Andreyevich Nyuktikov. In parallel, an aircraft designated 94-1 was built with a TV-2M turboprop engine, which was installed in place of one of the main engines together with a new nose section about 23 feet in length. At the Flight Research Institute, together with the Omsk radio plant, a new radio site for controlling the onboard guns was also tested on the Tu-4. It became the basis for the Production Defensive Control System PRS-1 Argonne. The idea to use the Tu-4 to check the effectiveness of interceptor armament arose because of its foreign origin. For this purpose, a special stand was created to simulate an aerial target. The Tu-4 airframe was placed in it, and test firings were conducted. At that time, it was concluded, albeit not entirely substantiated, that to destroy the American bomber B-47, a single hit by a shell of 1.5 inches in caliber in the central part of the wing would be sufficient. The effects of nuclear blast factors were also studied on the Tu-4. The Tu-4 became the first Soviet strategic aircraft. The only country to which it was supplied was China, the main ally of the Soviet Union in those years. China received 25 aircraft produced at Soviet factories in 1953. Crews trained on site under the guidance of the Soviet pilot Alexander Andreyevich Belenko. From the Chinese side, the training was overseen by the Minister of Defense, Marshal Juda. The stay of Soviet instructors in China began with an audience with Mao Zedong, where Soviet officers were even shown a Taiwanese newspaper reporting on their arrival and offering a monetary reward for Belenko's head. Training began with the imposition of strict discipline and overcoming the language barrier. Chinese pilots proved to be diligent. They compensated for lack of formal education with hard work. However, the system of punishments was quite severe. If a miss occurred during a training bombing run, the crew had to explain at the general formation why fuel and engine resources had been wasted. If the explanation was unsatisfactory, all crew members were sent to the guardhouse for 2 hours to think, after which the formation was repeated. One of the few breaches of discipline was that Chinese cadets ate their rations immediately after reaching altitude. To put an end to this, an order was issued. Chocolate was permitted to be eaten only after the bombing run, and only if it had been confirmed that the bombs hit the target. Meanwhile, the situation in the region remained tense. The war in Korea continued, and conflicts around Taiwan showed no signs of easing. Training had not yet been completed, but the Tu-4 was already being used for combat missions against Taiwanese targets. In official documents, these flights were described as training missions with live bombing. At first, the crews were commanded by Soviet pilots. The Chinese side highly appreciated the work of the Soviet instructors. For example, Belenko received a car as a gift, and after returning to the Soviet Union in 1954, he was awarded the Order of the Red Banner. He had completed at least 4 combat sorties over Taiwan. In China, the Tu-4 was being prepared to serve as a carrier for nuclear weapons, but the program dragged on. In 1957, the Soviet Union began transferring documentation for the Tu-16, and it seemed that the Tu-4 would soon be withdrawn from service. However, due to political changes in relations between the two countries and the failed Great Leap Forward campaign, China was unable to quickly master the new technology, and the service life of the Tu-4 was extended. The bomber was modernized, copies of Soviet systems were installed, the chrome-nickel identification system, the Siren 2 warning station, and other equipment. The shortage of engines remained a problem. It was solved in an original way. In the mid-70s, some aircraft received new power plants, the same as those used on the Chinese Y-8 transport aircraft, which was based on the Soviet An-12. It had 4 turboprop engines with a total output of about 4,250 horsepower. By the late 70s, using the Tu-4 as a bomber no longer made sense. In 1978, several aircraft were converted for launching WZ-5 drones from the air, and one was adapted for testing an airborne early warning and electronic countermeasure system. Even in 1991, the Chinese Air Force still operated no fewer than 15 Tu-4 aircraft. 2 of them in China and 1 in the Soviet Union, now in Russia, became museum exhibits, concluding the long and eventful history of this aircraft.